Okay, so in this video, we're going to talk about what is called the Chatliers Principle, which is what happens when you go messing with a reaction at equilibrium. The overall statement of Le Chatelier's principle, the technical statement of it is, if you have a system at equilibrium and you subject it to some stress, the reaction is going to move in such a way that it counteracts the stress that you added in. Right? So, for example, the common one that we're going to use is if you were to add a reactant into the solution. So, if you have your equilibrium mixture and you add in more reactant, the reaction is going to shift in such a way that it uses up that extra reactant. Right? So, it's going to want to go back to its equilibrium state from whatever you did to change it. Right? So, basically, what we're saying is if you disturb an equilibrium, the reaction will reestablish equilibrium. Right? That's the basic form of that statement. Now, there are some very common things that we can talk about with this. Right? So, we'll talk about common types of shifts that we'll work with and how you should explain this, because the explanation is actually going to be very specific for what the AP exam wants. Now, the reason why we know this is if we look at, say, for example, the formation of ammonia. This is the Haber process. The formation of ammonia has a very, very, very small equilibrium constant. It is highly reactant favored. Now, the thing is, the Haber process is a series of things that we can do to this reaction in order to make the reaction occur in measurable amounts. So even though it's highly reactant favored, we can get it to be very useful and produce a lot of product for us. Right? So one of the ways we do this is we keep pumping reactants into the system. And we'll think about this in terms of rates, right? So if we pump in more hydrogen, so if we have an equilibrium mixture of ammonia, hydrogen, and nitrogen, adding more hydrogen increases the concentration of the reactants. That means that the rate of the reaction is going to be faster because, again, rate law is determined by concentrations. Right? So if the forward reaction is going faster than it was previously, we're going to start producing more and more NH3. And eventually, the forward reaction will slow down while the reverse reaction speeds up, and we'll establish a new equilibrium, which is going to have more product than it did to begin with. Right? So there will be new concentrations. If the temperature of the process remains the same, the value of K will always remain the same. The concentrations will just readjust to keep that same ratio. Right, so here's what we were just saying. We added some hydrogen to our equilibrium mixture. When we add hydrogen, the forward reaction speeds up, which means we produce more NH3. So notice how, again, we added hydrogen here. When we did, the concentration of NH3 starts to increase as the reaction rate increases. And the reaction rate of N2 decreases because we're using it up, right? So we're going to use up the N2 to react with H2. And eventually, at some point, the reaction rates will become equal again, and our concentrations will remain the same. Right, so these are general shifts, and keep in mind, if you are doing the opposite shift or the opposite change, it will shift in the opposite direction. Right, so if you increase an amount of something, the reaction will shift away from the thing that you increased. Right? So again, if we increase hydrogen, which is a reactant, the reaction will shift towards products. If I increase the amount of ammonia in the mixture, the reaction would have shifted back to the left towards the reactants. Similarly, if we decrease the amount of something, it will shift towards that substance. So one of the ways that the Haber process makes this happen is not only does it constantly pump in nitrogen and hydrogen to increase their concentrations, but it will also liquefy the ammonia that's formed to reduce its concentration. Because remember, liquids aren't part of an equilibrium expression. Right? So all of that will cause the reaction to shift massively towards making more ammonia. If you change the pressure, increasing the pressure will shift to the side with less moles of gas. That makes sense, right? Pressure is proportional to the number of moles of gas in the system. So if we increase the pressure, the easiest way to reduce it is to go to the side that has less gas. Right? So again, our reaction, if you do it at a very high pressure, you had 4 moles of reactants, because 1 nitrogen, 3 hydrogens, 2 moles of gaseous product. So if you do it at a high pressure, our Haber process, the reaction will shift towards the ammonia side because that will alleviate the increase in pressure. Also, if you increase the temperature, increasing the temperature, you can think of temperature, so the way to think of temperature is think of temperature as a reactant or a product. Right? So for example, let's do a combustion. We'll just say combustion of propane because it's an easy reaction to remember. Right, so 3CO2 plus 4H2O. Right, so our combustion of propane, this reaction is exothermic. So that means that we can consider heat as a product of this reaction because it's given off. Right, so if we increase the temperature of this reaction, if it happens to be reversible, if we increase the temperature, it would shift towards the direction that used up the heat. So it would use the heat as a reactant and shift farther back to the left. Now, one other thing to keep in mind is that, again, equilibrium constants are only at specific temperatures. So if you change the temperature, the constant itself will change. And the last thing you could do is if you add a catalyst, there's no change in the reaction. Catalysts do not affect the thermodynamics of the reaction at all. All they do is get you to the endpoint faster. Same thing for equilibrium. It will not affect the equilibrium position of the reaction. All it does is get you to that point quicker. Right? So these are the types of changes that we're going to work with Le Chatliers principle. I'm saying shift towards or shift away. You'll also see referred to as shift to the right or shift to the left. This is generally not how you want to explain anything. Right? This is a good conceptual model to let you know which way a reaction will go, but the actual way that you want to explain this is you want to compare the values of Q and K. Because remember, you had your reaction at equilibrium, then you made a change. Since you're no longer at equilibrium, now you're working with Q. If Q is less than K, then that means that you don't have enough products to meet that equilibrium expression. So the reaction is going to shift towards products in order to balance that out. If Q is greater than K, then you have too much product, so the reaction will shift towards reactants. Right? So what you want to do is whenever you're asked to explain which direction will the reaction shift, you'll either say the reaction will shift towards products or towards reactants, because either Q is greater than K or less than K, depending on which change you're working with. If they ask you to justify your reaction or justify it, then you will actually go through and write out the change in expressions. Right? But you always want to explain Le Chatliers principle with Q and K. There have been questions in the AP exam since 2013 where they've asked you to predict the direction of the shift, and if you did not specifically mention Q versus K, you did not receive any credit for it. Right, so please make sure that you keep that in mind.